Enterprise software development has a scaling problem. AI tools generate code in seconds, pushing developer speeds higher than ever. Yet, when we measure overall business impact and delivery times, the needle is barely moving. The velocity of generation is crashing into a bottleneck. The friction comes from how the industry implements these tools. Engineering teams are treating AI as a faster typewriter, a localized assistant operating within the traditional, sequential software development lifecycle. This approach does not eliminate the development bottleneck, it just moves it. This diagram models a standard SDLC pipeline. When a developer queries an AI assistant, code is generated at up to 5 times the normal rate. But watch what happens at the review node. Human reviewers now have to process massive volumes of machine-generated logic. Because the generation engine is moving faster than the verification process, human reviewers are overwhelmed. Industry surveys show review times spiking by as much as 91%. The system is cracking under its own volume, and unverified code is leaking directly into production. Treating an AI model as just another developer tool is an architectural error. It falsely inflates engineering velocity metrics while actively compromising the stability of the production environment. When saturated human reviewers cannot keep up, the result is technical debt. Unverified AI-authored code integrates into the main branch, carrying hidden vulnerabilities and maintenance flaws that will cost time and money to fix later. This is a measured reality. Recent large-scale empirical studies have analyzed hundreds of thousands of AI-authored commits across thousands of production repositories, proving a direct correlation between AI coding assistants and accumulating technical debt. Safeguarding the production environment requires moving beyond the sequential SDLC. The necessary replacement is an AI-driven development lifecycle, or AI-DLC, where automated workflows handle both generation and evaluation. The challenge for modern engineering leadership is building a structure verifying code with the same speed and rigor as the models used to generate it. Researchers recently analyzed over 300,000 verified AI-authored commits across 6,000 GitHub repositories, tracking output from tools like GitHub Copilot, Cursor, and Claude. This cascading tree map visualization tracks the exact volume of technical debt identified in those commits. Out of the initial pool of over 302,000 commits, static analysis identified over 484,000 distinct issues injected by AI, divided into 3 specific categories. Look at this primary block. 89.3% of all issues are code smells. These are maintainability problems, like broad exception handling or unused variables, that make future updates slower and debugging more expensive. The remaining segments represent immediate operational risks. 6.0% are correctness issues, such as undefined variables that trigger runtime errors. 4.7% are direct security vulnerabilities, like path traversals or unsafe string formatting. The most alarming data point from the study tracks the lifespan of these errors. As this timeline overlay shows, nearly 23% of these AI-introduced issues survive past code review and persist in the latest repository revision. The math is straightforward. A linear, human-centric verification model cannot scale fast enough to catch the sheer volume of technical debt generated by non-deterministic models. To understand how this aggregate data behaves in a live environment, we can examine a specific case from the open-source proxy project Hysteria 2. This graphic shows a Python subprocess call written by GitHub Copilot. Notice the shell equals true argument. By adding this single flag, the AI introduced a severe command injection vulnerability into the network stack. This vulnerability bypassed initial review and sat fully exposed in the production codebase. It remained there until a human maintainer manually discovered the risk and patched it weeks later. This exposes a single-agent prompting flaw. Language models carry intrinsic blind spots regarding security context. When developers overtrust these models, they accept output without deep inspection. This leads to a core requirement for automated pipelines. The agent that generates an engineering artifact cannot be the same entity that approves its safety. The structural solution to this bottleneck is the AI-driven development lifecycle. Instead of giving broad instructions to a single coding agent, organizations deploy a decomposed multi-agent architecture. This node-based architecture graph illustrates the workflow. It starts by capturing human intent on the left, but instead of routing directly to code generation, the requirement feeds into a dedicated planning agent. The planning agent assigns the expected outcomes, establishes strict boundaries on scope, and isolates the execution environment so the system knows exactly what constitutes success or failure. From there, execution splits across specialized agents. A front-end agent, a back-end agent, and a test generation agent can now process their specific tasks in parallel, increasing actual delivery velocity. Before any of this output reaches a human, it must pass through the mandatory control mechanism of the SDLC, the independent critique agent. The critique agent has a specific adversarial mandate. It evaluates the generated code strictly to find functional gaps, security deviations, and unapproved scope expansion. By shifting the burden of initial line-by-line review from saturated human engineers to specialized evaluator agents, the multi-agent structure successfully breaks the SDLC bottleneck. Deploying a critique agent adds contextual judgment, but it does not replace traditional engineering controls. As we add this CI/CD gate node to our graph, we see the next requirement of the SDLC. The system relies on strict, unyielding deterministic tests, static analysis, linting, and dependency scanning to catch quantifiable errors that generative models might hallucinate past. Even with these layers, agents suffer from context starvation. If an agent only has access to the immediate source code, it will make poor architectural decisions. To solve this, we introduce a context repository that feeds data directly into the execution and critique workflows. This repository must contain machine-readable architectural decision records, API standards, and explicit business rules, providing the agents with the operational memory of the entire organization. Autonomous execution is only as reliable as the deterministic guardrails and contextual intelligence engineered around it. The AI-native SDLC elevates the human engineer's time to a new level of strategic value. This top-down architectural view represents the new perspective of the engineer. The human transitions from being a line-by-line syntax generator caught inside the execution loop to an orchestrator managing the workflow from above. The new mandate requires humans to focus entirely on defining architectural intent, setting rigid system constraints, and applying nuanced product judgment that machines cannot simulate. Even as agents execute the technical implementation, accountability for operational risk, security compliance, and final release decisions remains an exclusively human domain. The most resilient engineering teams will be those that successfully architect continuous, agentic learning systems that sense, decide, and act with explicit human accountability.